Welcome to The Explainer. Today, we're not just building a model, we're learning how to trust it. We're going to give our linear regression model a full health check, from its basic vitals all the way to advanced blood work.
Building a linear regression model can be, well, deceptively easy. A few lines of code and poof, you've got predictions. But how do you really know if those predictions are reliable, right? How can you be sure the story it's telling is the true story?
Because let's face it, a bad model, one that's built on a shaky foundation or has some hidden sickness, it can lead to some disastrously wrong conclusions. And that means very costly mistakes. That's exactly why we need to perform a thorough health check before we ever act on its advice.
Okay, so let's dive right in. Here's our game plan for today's diagnostic session. We'll start with a quick sanity check, then grade its performance, run some deep diagnostic tests, translate all that math into action, and wrap it up with a super handy checklist you can use.
All right, first things first. Before we get into any of the heavy-duty modeling, we've got to do an initial consultation on our data. Think of this as checking the patient's basic vital signs.
So, we're going to start with the single most important question you can possibly ask. Is there even a relationship here worth modeling in the first place? I mean, really? And the correlation coefficient? It gives us a quick and really powerful answer to that question. Now, this slide does a fantastic job of translating a kind of abstract statistical score into a real-world story. So you see a score near +1, like that 0.9 for distance and time. That shows a strong, predictable relationship. Makes sense, right? Then you've got a score near 0 for something like, customer shoe size, which just confirms what we already guessed. It's just noise. And then a strong negative score shows that inverse relationship. As one thing goes up, the other goes down. Like how increasing speed decreases delivery time. So this one little number, it quickly tells us the direction and the strength of the story hidden in our data.
So, here's the crucial takeaway. This acts as our go or no-go gauge. It's that simple. If you find there's basically no correlation, you stop right then and there. A linear regression model just can't magically create a relationship that doesn't exist in the data to begin with. Okay, let's move on. Assuming our data passed that initial sanity check, we can now build the model and give it a proper fitness score. We're basically putting it on the treadmill to see how it performs under pressure.
Okay, so to grade our model, first we need a baseline. We need to know how much total chaos or, variation exists in our data. Think of it like this. What's the total error we'd have if we just guessed the average every single time? That's our baseline, our score to beat. That's SST. Then we build our model and see how much of that chaos it can explain. The error that's left over, that's the SSE. The whole goal here is to see how much of that initial mess our model managed to clean up.
And now, we turn that comparison into a grade. By looking at how big that initial chaos was versus how much error is left after our model did its thing, we calculate a score. And that score is called R-squared. In this case, our model scored a 0.85. That's our performance grade.
And hey, an R-squared of 0.85? That is a great score. It means our model has successfully explained 85% of that total chaos we started with. It basically turned a huge pile of uncertainty into a predictable pattern. That is some strong performance right there. A score close to 1 is definitely what we're aiming for.
But hang on, a quick word of caution here. If your model is using more than just one input variable, you absolutely need to look at the adjusted R-squared. Why? Well, because the regular R-squared will almost always go up every time you add a new variable, even if that variable is completely useless. Adjusted R-squared is smarter. It actually penalizes the model for adding junk, giving you a much more honest score.
All right, our model seems pretty fit so far, but now it's time for the real heart of the health check. We need to run the advanced diagnostics. The blood tests, the scans, to look for those hidden diseases that could make our model completely unreliable down the road.
Okay, first test up is for statistical significance. We need to check if each ingredient, each variable in our model, is actually contributing in a meaningful way, or if it's just, random noise. And we do this by looking at its p-value. And the rule here is super simple, very direct. The standard threshold is 0.05. If a variable's p-value is less than that, it's a keeper. It's doing good work. If it's higher though, it's statistically useless. You should drop it from the model and rerun your analysis. Next up, we check for a condition called multicollinearity. Sounds complicated, but it's not. This is just where your input variables are redundant. They're essentially fighting each other, which makes the model unstable.
A classic example would be including both distance in miles and distance in kilometers in the same model. To catch this, we use a metric called the variance inflation factor, or a VIF for short.
So, we measure this with the VIF score. A good rule of thumb is that if any variable has a VIF score greater than 4, it's probably redundant. It's time to remove one of those overlapping variables to make your model much more stable and reliable.
Okay, this next test is a visual one. We need to check if our model's errors are consistent across all its predictions. Like, does it make small errors for small predictions and also small errors for large predictions? Or do its errors get wildly unpredictable as the numbers get bigger?
So if you plot the model's errors, we call this a residual plot, what you want to see is a random, formless cloud of points. That's a healthy sign. But if you see a megaphone shape, that's a huge red flag. It means your model's predictions for large values just can't be trusted. And hey, while you're looking at this plot, you should also be scanning for another problem, outliers. These are those single data points that are so extreme they might be warping your entire model. We can actually measure their influence with a score called Cook's distance. A high score there means a single point is pulling your model way off course, and it definitely needs to be investigated.
Okay, our model has passed all its tests. It's been declared healthy. Now for what I think is the most important part, translating all those mathematical results into clear, actionable advice for the business.
This is really where the math turns into money. The coefficient for each variable tells you its exact, real-world impact. It's amazing. So if the model's math spits out a coefficient of 2.5 for distance, that's not just a number. It's a powerful business rule that says, hey, for every extra kilometer of distance, we can expect delivery time to increase by 2.5 minutes. Now that is something you can take to the bank. That's a real, actionable insight.
And finally, a really crucial rule for communicating your results. Never, ever state a prediction as a single certain number. Every model has some level of uncertainty, right? You should always report your findings as a confidence interval. It's just more honest, and frankly, it's far more useful for actual decision-making.
So, to bring this all together, here is your final cheat sheet. This is the whole process in one place. We covered that initial sanity check with correlation, grading the fit with adjusted R-squared, checking for significance with p-values, looking for redundancy with VIF, and ensuring stability with the residual plot. And of course, we talked about checking for those influential outliers using Cook's distance to spot any points that might be warping your model. This table right here guides you through the entire diagnostic process from start to finish.
Because you got to remember, a healthy, trustworthy model, that's not the end goal. It's actually the powerful tool that gets you to the beginning of making smarter, more confident, data-driven decisions.